So hi everyone, thanks for being here. I'm Marco, and in July 2024, I was hired by the Rust Foundation to join the infrastructure team of the Rust project full-time. And today, I want to share with you how I made the Rust CI dramatically cheaper, so the CI of the Rust compiler. This is my GitHub and picture. And so first I will show you what the Rust CI is and how it works, the optimizations that we did to make it cheaper, and how we're looking today. So let's start. We can define continuous integration as a set of jobs that runs when there is an event in the code base. So for example, when a contributor opens APR or pushes commits to it, the continuous integration runs. If the tests fail, the contributor can push more commits, and once the test passes, the PR is ready to be reviewed and eventually get merged to the Rust repository. So we have two types of CI jobs, pull request jobs and the auto build. Pull request jobs run immediately when a contributor commits to a PR or opens a new one, and they catch errors early so that we prevent the auto build to fail. The auto build is a set of many jobs, 84 now, and they run in parallel whenever we want to attempt to merge something to the Rust default branch. We say that PR jobs run as soon as somebody submits code. So they are there to give fast feedback to the contributors and run like in parallel, because there are many people working on the Rust compiler at the same time. While the auto builds are queued, so they run sequentially, and contributors after their PR is approved, it might take 1 or 2 days even before their PR is attempted to be merged by running an auto build. So that's why we try to prevent errors early with PR jobs. So what the auto build does depends on the importance of the target. So for tier 2 targets, we build all the artifacts, so like the Rust compiler, cargo, Clippy, and so on, and we upload them to the cloud where we can download them via Rust app. For tier 1 targets, we do the same, but we also guarantee that we run all the tests in the Rust repository, so like the test of the compiler and so on. So if we sum all the CPU time of those 84 jobs that we saw before, we get that one auto build takes 150 hours to run. So it means that whenever we want to attempt to merge something to the Rust compiler code base, 6 days of CPU is involved. Of course, this isn't how long a contributor needs to wait to know if their build passes, because these jobs, we say they run in parallel, so the duration of the auto build is given by the slowest job. So nowadays is around 3 hours. And so this means that if we want to make the auto build faster, we need to make the slowest job faster. If we take a random job that takes 1 hour and we make it 30 minutes, we don't gain that much. And this doesn't mean that we can merge at most 1 PR every 3 hours. We have roll-ups. So people in the project select PRs, and they attempt the auto build on all of them. And in case the auto build succeeds, we merge all those PRs at once. So we all like numbers. Let's see how many minutes of CI, of CPU time we spend every month in the Rustlang repository. Well, yeah, for July, for example, across all the jobs that run in the Rustlang organization, so this includes other repositories such as Cargo, Clippy, we took 3 million minutes, which is 6 years of CPU time. So for every month, the Rustlang organization yeah, we spend 6 years of CPU time. It's crazy. Like maybe you're wondering, where's the problem in all of this? So when it comes to CI, we have 3 constraints mainly. The first one is time. We want the CI to be fast enough. We don't want those 3 hours to become 10. We need resources, so we need hardware to run those jobs and like these runners need to have enough disk space, enough RAM, and so on. And of course, we don't want to pay too much for CI. And yeah, as you can imagine, cost, of course, is the constraint that is most pressing for us. And maybe you're wondering, but wait a minute, aren't GitHub Actions free for open source? Well, kind of. So GitHub, if you go to the settings of a free organization, you'll see this mini dashboard that shows that GitHub offers 20 standard runners concurrently. But we already saw that just for the Rust repository, this is for the entire organization, but just for the Rust repository, the auto build needs 84 jobs at the same time. So of course, this is not enough for us. Plus, some standard runners might be not powerful enough for some of our jobs, especially if we want some reasonable times. So in this case, like when we need more powerful machine, we use GitHub large runners. So for example, standard runners have 4 cores, while large runners have up to 96. Standard runners come with 14 gigabytes of available disk space, while large runners can have up to 2 terabytes. And yeah, of course, the big difference is that standard runners are free, up to 20 running at the same time, while large runners, they come with a per minute rate. For example, these are the prices up to today, as of today. And these are some of the large runners that we use or we used in the past. So if we take the per minute rate and we multiply the number of minutes of CPU time of all the large runners of the auto build, we get that as of October, basically whenever we, the cost of attempting to merge something to the default branch of Rust was $141. So this was in October, before the optimization work started. If you sum all the auto builds in the month and all the PR jobs and all the large runners we use, the cost was $47,000. So we used the large runners for a while they were in beta, but like now they are stable. And so it was time to formalize our sponsorship with GitHub. So in Q1 this year, the Rust Foundation signed a multi-year agreement with GitHub where we got some nice stuff. First of all, we get 500 concurrent standard runners, which compared to the 20 that GitHub gives in the free plan, they are much more. And they also gave us a discount on the large runners. Plus, they helped us to get some sponsorship from Microsoft to cover some of the remaining costs with Azure credits. So, we have these large runners that comes at the cost. However, we have 500 standard runners that are free for us. They are given to us for free. So we started an optimization work in around October, where we tried to move as many large runners as possible to standard runners. So after this introduction of the Rust CI, let's see what optimizations we did. When we started, 33 out of 60 jobs were running on large runners. So for example, we had 11 runners that are Windows 8 core, 10 Linux 8 core, and so on. We did 4 kinds of optimizations. So the first one is we tried to convert over-provisioned jobs. What does it mean? We say that the auto build, the duration of the auto build is given by the slowest job. So if the slowest job takes 3 hours, And for example, there is a job that runs on a large runner that takes 1 hour and a half. What happens if we move this job to a standard runner? If this job on the standard runner takes less than the slowest job, then it means that it's totally acceptable if that job takes a bit longer, because yeah, we are already waiting for the slowest job. And so yeah, we converted all these over-provisioned jobs. Converting, like moving the runner for one job is as easy as changing one line. So this made quite easy to run these experiments. And so with this technique, we removed 7 large runners, and we have 26 to go. Maybe you're thinking why there was this inefficiency in the first place. Yeah, we were wasting resources, and I'll give you 2 reasons for this. The first one is that the infrastructure team is quite small. We are 7 people. We have to maintain so much stuff, not only CI, and in fact, many volunteers of the team don't even work on CI, I mean. Plus, the bottleneck of 3 hours changed with time. For example, 2 years ago, it was 2 hours. So yeah, nobody basically did this job of verifying that we could move large runners to standard runners. Sometimes, yeah, this process was a bit more involved. I found out the hard way that when you change the runner of a job, you invalidate the cache. So we cache a bunch of stuff in the Rust CI. One example is LLVM. Whenever there is a cache miss, the job needs to recompile LLVM, which takes time, of course. So what I did is attempt the same job twice after moving to the new runner, so that the second time I got a cache hit and I could compare, let's say, apples to apples, because yeah, the 3 hours is on a cache hit, because most of the time we get cache hits. And sometimes the first attempt, yeah, cache miss, but sometimes even the second attempt got cache miss, and that was because in the meantime GitHub was rolling out new image runners. So yeah, again, found out the hard way. But yeah, by trying more than once, we managed to remove 2 additional large runners. The second optimization we did was freeing up disk space. So we said that yeah, GitHub standard runners come with a guaranteed disk space of 14 gigabytes. So we were using 4 cores large runners just for the disk space. The number of cores and the RAM was the same. We managed to move to the standard runners by using this GitHub action. It's called the free disk space. And yeah, by doing this, we managed to remove 7 large runners. And yeah, that's because GitHub, in their runners, they pre-install a bunch of stuff that we didn't need, like the Haskell toolchain, a web browser, and whatever. In fact, we forked this action because it was unmaintained. We just forked the script, and we managed to remove even more stuff than what the action was removing. In total, we removed 37 gigabytes, and yeah, in this way, freeing up more disk space, we removed 3 additional large runners. In the diagram, there is only 1, because in the meantime, 2 runners were reverted from standard to large runners. So here I'm telling you like a linear history, but of course the Rust compiler is a moving target. Like people always add new tests, there are new stuff to download and so on. So yeah, sometimes we did a bit of back and forth between standard and large runners. So yeah, the third optimization is probably the most interesting, which is splitting jobs. So we analyzed how much time each job spends between building the artifacts and testing them. And we found that actually testing the artifacts is where most of the jobs spend their time. So what we did was we replaced one large runner with 2 standard runners. Of course, building the artifacts now takes a bit longer, but each standard runner runs half of the test suite. So in this case, we can get rid of one large runner by replacing it with 2 or more standard runners. Of course, this approach comes with an inefficiency, because you see that we build the artifacts twice. Basically, we do the same thing twice. And this can be solved with fanout. This is something that we could implement in the future if you want. So instead of 2 runners building the artifacts, one runner builds the artifacts, and it compresses them and uploads them to a bucket in the cloud. Then 2 standard runners downloads these artifacts, decompress them, and run the test suite as before. So you can see that now we only build the artifacts once. Why we didn't do this yet? First, this, of course, introduces additional complexity, and people in the team who already implemented this for the Rust compiler, but in another CI, told us that it's not as easy as it looks like in the diagrams. Plus, it will take engineering time to implement and maintain this. And finally, this makes the overall job slower, because these arrows that you see, they mean additional latency. It takes time to compress and upload, and to download and decompress all these artifacts. So with this technique, we removed 12 large runners, and we just have 6 to go. And this is only for the auto build, by the way. We also have add large runners in PRs, but with this technique, we managed to remove all the large runners from PR jobs. So you can go crazy and contribute to the Rust compiler, because we just use standard runners in PRs. OK, so the last optimization is probably the simplest. So in January, GitHub announced that they made available Linux ARM runners for free repositories, for public repositories. And what we did was move from our ARM large runner to the standard one. Very simple. And with this approach, we removed 3 large runners. One was reverted in the meantime, but overall, great stuff. Let's see how we're doing today after all these optimizations. So we started these optimizations in October last year, and we roughly finished on around May with various degree of hours spent on this project. We started with 33 large runners, and in May we have 4 large runners, so 77 standard runners. So the cost went down from $141 to $34. So in May, we pay, since May, let's say, we pay 25% of what was, sorry, let me rephrase it. So in May, the cost went down, and the cost is now 25% of the cost of October. Yay. We started also using AWS Code Build, which is an AWS alternative to GitHub large runners. So basically, instead of runs on and the name of the runner, you just substitute the name of the runner with the code build Ubuntu. And the workflow runs entirely in AWS instead of GitHub. So these are the large runners that remained in GitHub. What we did was move one of them to AWS, and this was a huge win for us, because like we verified that our vendor lock-in in GitHub Action is not that much. Of course, we need to use the GitHub Action workflows, syntax, and so on. But nowadays, many cloud providers offer alternatives to the GitHub runners. And so, yeah, basically what we can do is move from one cloud provider to another, depending on which credits we want to use. And yeah, I didn't mention this, but yeah, AWS, it's been a few years that they provide the Rust project credits to run their infra on. Speaking about credits, we also got a sponsorship from Microsoft, where they gave us enough credits to cover those remaining runners that we saw on GitHub. So yeah, overall, we're doing fine. And yeah, let's see what the future of the CI looks like. I mean, the usage of the CI grows like constantly. We said that 2 years ago the auto build was taking 2 hours. Now it takes 3 hours. Of course, it cannot grow like that forever. And yeah, we are always adding new targets, new tests, and so on. So it's going to be challenging. But at least now we signed this agreement with GitHub, which, yeah, we have written down what resources we have, and we can plan around that to know what we have and what we can do in the future. So in particular, we created a repository called CI Feedback, where, yeah, together with the rest of the Rust project, we want to think about how we can improve the CI from first principle. So, for example, these are some of the GitHub discussions that we opened. We want to add the ability to reproduce Windows and Mac CI jobs locally, although it's very difficult, and for now we don't really know how. We want to categorize CI failures, so understand that, for example, I don't know, what's the percentage of auto build that fails due to flaky tests? I don't know, stuff like that. Or understand what tasks each job executes, or having alerts when the CI takes too long, improving the observability, and so on. Yeah, so efforts like this from the infra team, they happen quite a lot, but often they are less visible with respect to other efforts coming from other teams, because maybe they are less user-facing. And so, yeah, I wanted to give this talk to underline this effort. And yeah, because like stuff like that, it's even if it's not user-facing, it's still very important to keep the lights on. This is the infra team. I would like each person in the team helped in one way or another. So thank you for everything. But yeah, if I need to thank one person in particular, that will be Jakub Beranek. The username is Kobzol. He reviewed, I think, more than 90% of the PRs that you saw listed in the slides, and he gave me so many ideas on how to improve stuff. So thanks a lot. And yeah, very well deserved, yeah. He also has a blog, you can check it out. Yeah, so finally, if you want to help us, we are, of course, always looking for volunteers. We maintain so much stuff, not only the CI. We have Rust, bots, infrastructure as code, I don't know, so many things, yeah. You can write to me if you're interested. Thanks.